Hello, and welcome to another edition of the 2023 Von Kármán Talks. My name is Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for this evening's discussion on the Earth Surface Mineral Dust Source Investigation, better known as EMIT. EMIT launched July 14, 2022, and observes the Earth from the International Space Station today, studying mineral rock dust blown by the wind and suspended in the air, which can affect the heating and cooling of the atmosphere and Earth's surface. EMIT is also capable of mapping super emitters of methane, which is already contributing to meaningful climate action. Now, joining us as co-host this evening is Jocelyn Argueta. Jocelyn is a public outreach specialist for NASA Earth, where she shares stories of how NASA data helps us learn more about our home planet. So, hi, Jocelyn. How are you today?
Hi, Nikki. So great to be here tonight. And I want to remind everyone watching that this is your space program, and we want you involved in the conversation tonight. So wherever you're watching us from, please ask your questions in the chat box, and our social media team is going to bring in as many as we can fit into our talk tonight. If you don't see your chat box, then reload your page, and it'll be right there.
Awesome. Thank you, Jocelyn. It's great to have you as always. Now, I want to remind our audience, if we do run into any technical difficulties or small failures, we please ask your patience and stick with us. We'll get them sorted out as quickly as we can. And now, let's introduce our speaker for this evening. Dr. Robert O. Green is a senior research scientist, JPL fellow, and director of the JPL Microdevices Laboratory. He was the principal investigator for AVERIS and the instrument scientist for the NASA Moon Mineralogy Mapper. He is also a science co-investigator on the Mapping Imaging Spectrometer for Europa, better known as MISE, and the NASA Lunar Trailblazer mission. Dr. Green is also the instrument scientist for the Carbon Plume Mapper Imaging Spectrometer and has worked with imaging spectrometer instrumentation for more than 25 years. Hiya, Rob. It's great to have you tonight.
It's wonderful to be here. Great to see you all.
Thanks for being here. So, you've been working towards this for over 25 years. So tell us a little bit, how did you get into this field and at your position currently with EMIT?
It's a wonderful story for me. It began in graduate school at Stanford University. I was studying for a graduate degree in geology, and I was out in Nevada learning to map minerals and realized there were new technologies coming that could allow us to map minerals directly from their spectroscopic signatures. And a spectroscopic signature is just the way that mineral reflects light at many, many wavelengths, from the visible out into the infrared, that the molecules of those minerals, they absorb light differently at different wavelengths. So it becomes a fingerprint of different minerals. So I understood that there was a new approach, something called imaging spectroscopy, where you could build a new instrument that measured a spectrum for every point in that image and then map the minerals based on their spectral signatures or their spectral fingerprints. And that's where I got inspired. I learned JPL was building the very first imaging spectrometer called the airborne imaging spectrometer, and soon a follow-on instrument called AVERIS. And that drew me to come to JPL and to learn about this new measurement technique. And I've been able to work with it through now more than 25 years with increasingly sophisticated instruments, and brought me to my current position.
You are incredibly dedicated to the work that you're doing, and that is so honorable. Can you tell us, what is EMIT?
Okay, EMIT is an instrument designed to answer a specific question, but because it's answering that question, it can also answer other questions. It turns out that the Earth has a mineral dust cycle. When there are high winds blowing across arid lands, dust is emitted into the atmosphere, where it starts to interact with the Earth system. It immediately changes the chemistry of the atmosphere. It can play a role in how clouds are formed. It can scatter light back into space, those little mineral particles. It can absorb light if they're dark particles and heat the Earth. And then when it's deposited in terrestrial ecosystems, in plants on the surface, it can provide a nutrient. It does so for the Brazilian rainforests. When it lands in oceans, it can provide a nutrient. When it lands on snow, it can change how they melt. That impacts water resources here in California, for example. And then when it arrives in our cities as little dust particles, they can be a visibility hazard. They can also be a bit of a toxic hazard. So there's this important cycle of dust, and EMIT is designed to help us answer a really important question: is what is the dust made of? And because there are different minerals in different places of the earth, we want to know when the winds blow, what kind of particles are being blown into the atmosphere. Are they light particles, dark particles, more acidic particles, more basic particles? And how are those going to interact with our Earth system? And I can show just an example. If we bring up one of the charts you prepared for me, I just have to grab the one with the conveyor belt. That would be ideal. I believe it's chart 3. Thank you. Yeah. So this is in a nutshell the EMIT mission. We've got a situation where winds are blowing along the Earth's surface in arid lands. They launch that dust into the atmosphere. It can heat or cool the Earth. We call that radiative forcing. And then when it's deposited on the Earth, it can have all those effects that I talked about. So that's what EMIT is designed to help us understand this dust cycle. And the particular problem EMIT is tackling is that currently, when we model dust in the Earth system, we rely on only 5,000 measurements around planet Earth, for the whole planet, where we know the mineral for those locations. With EMIT's imaging spectroscopy, we can take that from 5,000 to 1 billion measurements all over the arid land and really improve our ability to understand radiative forcing and the other elements of mineral dust in the Earth system. So that's what EMIT is. It's an instrument to collect spectra for the arid land regions of our planet to address that important question of heating or cooling of our planet and the other interactions throughout the Earth system.
So it's great to know what EMIT does, but how does EMIT specifically study the spectral range of mineral dust? Why is this so important? What is the prime mission of EMIT?
So the prime mission really is to understand if mineral dust currently is heating or cooling our planet. We don't know whether it's heating or cooling. And then the secondary objective is to understand with these climate models, constrained by EMIT measurements, how will the dust cycle change in the future? Would there be more regions for mineral dust or less regions? And how will that impact the climate in the future? So it's got two climate objectives: understanding how dust is impacting our climate today and how it might impact our climate in the future.
And how is EMIT different than our past missions?
Okay, EMIT really is the first of its kind of this class of imaging spectrometer. We brought technology that's only just become available. Even though we did the first imaging spectrometer quite a while ago, this one has the very latest detector, the very latest design. It has very high signal to noise, or very high precision. We can see very small variations in minerals and other elements of the Earth system. So it's really the first of this next class of imaging spectrometer, and it's here to study our Earth with the focus on the EMIT science objectives, but it may also help with other science objectives.
So Rob, you just mentioned other science objectives. EMIT has also been able to study greenhouse gases in a new way. Was this something we were expecting, and can you tell me more about that?
Yes, this is an interesting added value from EMIT. We had to measure this spectral range where minerals absorb light so we could answer our question of what minerals are on the surface of the Earth. So that range sends us out into the short wavelength infrared, as we would call it. It turns out that the absorption of methane and carbon dioxide, these gases in the Earth system, also occur in this spectral range. So we thought there would be some sensitivity with EMIT when it was launched and began imaging our Earth. And it's turned out there is. It's better than our expectations. So we are now able to map plumes of methane coming from various point sources, and also carbon dioxide also coming from point sources. So we're seeing some new spectacular plumes. And I can jump to an image I would call image 11 will show you one of those examples of these additional benefits. So this is a data set from EMIT near the Caspian Sea. What you're seeing in the upper left are the plumes that we've mapped from the EMIT spectra in the spatial domains. You can see these large plumes. These are really extraordinary emissions of methane into our atmosphere. And then on the lower right, you're seeing the actual spectral fingerprint that was measured by EMIT. We measured that blue spectral fingerprint. We have a model that says what methane should look like, and that's red spectral fingerprint. You can see how well those fingerprints match so that we know we're seeing the molecule methane in the Earth's atmosphere. And we've now been asked by NASA to map the methane plumes that we see with EMIT and make those available for others to make decisions about how they might want to address these methane sources. And I think if we look at chart 14, you can see how well we've done with greenhouse gases with EMIT today. So these are the plumes of methane across 6 continents that EMIT has seen, even though it was launched less than a year ago. And we're up into many hundred plumes. And we're making this available to all who are interested to understand those plumes and think about how they might choose to address those methane occurrences.
Absolutely. And just so you folks know, what Rob is talking about is this is available online publicly to all of you. Our wonderful social media team is sharing some links in the chat with you. And this is one of the links that they'll be sharing throughout the lecture tonight for this interactive. You can check on it. This is a screenshot from yesterday, but it updates regularly, so you can check that online as well. So, Rob, what's next for EMIT? I mean, it sounds like it's already been doing incredible work, but what are you most looking forward to learning about because of EMIT?
Well, let me jump back a little bit to our prime objective, which is the mineralogy, and show you some of the things we're learning right now. And so I'll jump to image 9 if I could, and this will show an example of how we're doing just what we said we would do when we proposed this mission to NASA. At the lower left, you're seeing an image cube. That's an EMIT data set of more than 1 million spectra with a spectrum for each point in that image. And above there, you're seeing the radiance. That's the signature EMIT sees at the top of the atmosphere. So that's the fingerprint of the whole Earth system that's got the atmosphere and all elements of the surface. And then to the upper right, you're seeing once we peel back the atmosphere, now we have the spectral signatures of the minerals. So we can see iron oxide minerals, which are dark and could heat the Earth. And we can see evidence of clays and carbonates, which are brighter and could scatter light and have a cooling effect. And then down below in the middle and the right, you're seeing we're already producing these mineral maps for the Earth system. And again, each one of these cubes has 1 million measurements. And remember, we're trying to replace the current situation with only 5,000 measurements. And here we are beginning on that journey. And then to give you an idea of how far along, I'll ask that we bring up image 10. This is the amount of coverage EMIT has already collected on our planet in less than a year. You can see we've got large areas of blue. Those blue are orbit segments from the International Space Station where we've collected EMIT data sets. Each one of those blue stripes consists of a number of those little cubes, each cube having about 1 million spectra. And this is how far we are already in collecting that data set to update the Earth system models. So I'm very excited about achieving EMIT's primary objectives with this spectacular data set.
So it's awesome that we are achieving these great things, but there's a lot more things to come, right? We're looking at, we talked about greenhouse gases, but you also touched on water resources, mineral resources, studying the oceans and coral. I mean, this has so many applications, right, Rob?
Absolutely. The data set, while we're focused on the arid land regions, we collect adjacent data sets which have all these different signatures or fingerprints of the Earth system. So some related to snow and ice. When we capture those, we can understand, is there dust on the snow? What's the brightness of the snow? Is it going to melt more quickly or more slowly? So that relates to water resources and hydrology. In many of the arid land regions, when we're next to an ocean, that's often an area where there are coral reefs and seagrass. So the EMIT data set can be used, while not for the prime objective, scientists who are interested in using the EMIT data set to investigate important questions about aquatic systems, seagrass, coral reefs. And then there are terrestrial ecosystems around all these arid land systems, like we have here in California. And the spectral fingerprints of vegetation are also available for people to pose and answer questions and pursue applications. In fact, excitingly, NASA has just released an opportunity for scientists and others to propose to use these data sets and support their use of these data sets. And that's just been released in the last couple of weeks. So that will really grow the utility of these spectacular new measurements that really are first in their class in terms of their signal to noise and other excellent properties.
So what comes next after EMIT, Rob?
Yeah, that's where it's even more exciting. That the National Academy of Science Decadal Survey called for NASA to work on the next generation observations for our planet, and we call those part of the Earth System Observatory. One key element of that Earth System Observatory is called surface biology and geology, and it includes a wide swath imaging spectrometer of the EMIT type, except scaled to the next level, using the next level of technology. So SBG, or surface biology and geology, will map the entire Earth pole to pole every 16 days, and those data will allow us to take all these science and application objectives that we're testing with EMIT, that's risk reduction. We'll be able to use them now routinely into the future with the surface biology and geology data set. So I'm very excited about where we're going and how EMIT can play an important role in preparing us for that era of global coverage.
So you've talked about amazing Earth applications of this technology, but are there any outside of planet Earth?
Yes, absolutely. In fact, imaging spectroscopy is used throughout the solar system, and JPL is playing a major role right now. We just finished an instrument called the High Resolution Volatiles Minerals Moon Mapper, and that's part of the Lunar Trailblazer mission that will be launched to the moon fairly soon to look at the minerals on the moon and question of volatiles. That's water and materials like that. So that's the best way to answer that question quickly in the moon as we think about how humans will be interacting in the moon going forward. And then further out in the solar system, we're also building an imaging spectrometer called the Mapping Imaging Spectrometer for Europa. And that spectrometer will head out on a mission called Europa Clipper to look at that moon of Jupiter, which has an ocean under an ice shell. And we can look at the signatures of what's on the surface of that ice shell and perhaps answer some questions about habitability and some fairly interesting questions about what might be happening on an icy moon with an ocean below it, because some of that ocean periodically rises to the surface, is left on the surface. And of course, there has also been a spectrometer in orbit around Mars for quite a few years, though it just finished its mission in the last month or so.
Well, Rob, it sounds like there's a lot of great technology that can use this, or a lot of things that can use this. Through our many conversations, we've also talked a lot about the team, and so before we open up for Q&A, I do want to give you a moment to talk about that. I'm going to ask the team to start with image 6 for us, please, and you can flip through a couple of those and talk about the team behind EMIT.
Please. Again, it's an extraordinary team of well over 100 people. We spent 41 months building this instrument and getting it launched at the space station. This is a part of that process where we're attaching the telescope spectrometer system to the electronic system in the laboratory. So we're bringing down that upper thing. And here's the team following all the guidelines ever so carefully to bring this instrument together, to create this instrument from a large number of parts. And then if we can jump to the next image, it's really spectacular. This is another subset of the team. After the instrument is pulled together, we've got the telescope and the electronics bench below. Later, we'll go into a thermal enclosure. And then what came next, though I don't have all the intermediate shots, we can jump to the next image, which is image 8. This is actually an image of what happened in the period from the 14th of July to the 28th of July, 2022. That is EMIT, labeled on the space station, looking at our planet. This picture was taken by astronaut Jessica Watkins, and she kindly shared it with us. So all that work, that huge team for 41 months, really building this new state-of-the-art imaging spectrometer ended in spectacular success with EMIT arriving on the space station thanks to SpaceX and that spectacular team. And then the ISS team has been amazing taking care of EMIT. They provide us all our power and all our commanding, and all our data come down through the International Space Station system, and that's worked flawlessly. In some cases, we will make a measurement of Earth on one day, and within 24 hours, we will actually have mapped the minerals because of just the extraordinary teamwork involved in moving the data and processing the data and getting us to this amazing state.
That's incredible to hear, Rob. We've had a ton of great questions come through the chat. So, Jocelyn, I know they're excited. What is the audience asking of Rob?
Yeah, lots of really great questions out here, and you've given us a great overview of how EMIT works. And Con on Facebook wants to know, how is EMIT going to help us fight climate change caused by dust storms?
So what we can really do is EMIT can give you the information to make some decisions about how you might adjust land use, right? You could imagine how you use the land can create more cases where it's easier for dust to launch into the atmosphere or harder for dust to launch into the atmosphere. In fact, there's a great experiment in California at Owens Lake where they're looking, they know about the dust, and they're figuring out how they would modify the surface to try to minimize the dust that's launched into the atmosphere that again results in dust storms.
Great. Beth on LinkedIn is wondering, can this be used in disaster recovery, for example, after an eruption?
Yes, this can provide important information for disaster recovery and understanding disasters after volcanic eruptions. You could understand a number of things about where the dust particles went, where the damage was. We can see where the lava is flowing. There's information we can provide. We were actually used an airborne spectrometer after the Gulf oil spill to understand how much oil was on the water and how it would impact the ecosystem. So there's a large number of applications to address hazards and disaster response with this type of imaging spectroscopy. That will also be true in the future with the surface and biology and geology mission.
And continuing on that conversation of applications, Sarah on Facebook wants to know, will we be able to build predictive models with this data too? They're thinking about applications with some of the AI tools that currently exist. Yes,
I think absolutely. In fact, we're already using a little bit of machine learning and AI in some of our retrieval algorithms in emulators and things like that. So I think, yes, as this data set is giving a new comprehensive measurement of the Earth system, in those measurements are patterns, and they're not all the patterns that we can find quickly with our understanding of science and physics today, but things like machine learning and AI might help us discover those patterns more quickly, and then we can build models that are prognostic and more powerful than maybe we would have through some more traditional methods. So I'm very excited about the potential of this new data set with all the information content embedded in it and people taking advantage of that with machine learning and artificial intelligence.
And speaking about the measurements, Dee on YouTube is wondering, how much surface area does one measurement cover in square miles, square kilometers?
The one spectrum is about 60 by 60 meters, so you can think of it as a football field class observation. But there's something extraordinary about spectroscopy. If in that field you have only a quarter of it filled with one mineral, we can still see the spectral signature of that mineral, even though it's only occupying a quarter of that 60 by 60 meter. This is called spectral unmixing. So because that spectral signature is unique and present, we may not be able to say which quarter has that mineral, but we could say that mineral is there. So we have sort of a spectral zoom capability to look at concentrations of materials much smaller than the nominal spatial scale, and that's another powerful result of using high-fidelity spectroscopy.
And a great follow-up question here from Jenny on YouTube, which is, can EMIT tell the height of different particles or dust storms when those are airborne?
It's a little tricky. There are different ways to do that. Basically, we can look at shadowing effects and things along those lines, but we don't naturally have the vertical profile in the EMIT measurement. And again, the core EMIT measurement is to look at the composition of the source regions that get blown into the atmosphere so that we can make predictions. If it's coming from this location, is it likely to be maybe a toxic mineral, asbestos that happens in California, for example, or is it a mineral that's going to heat or cool the atmosphere? So mostly we're focused on the surface source regions that then we can use with different methodologies to predict where they might go and how they might interact with the Earth system, including ourselves.
And I've got to say, I love those photos of the instrument being built. And Amy on Facebook is wondering, were all of the elements of the EMIT instrument developed by JPL, or were other industry partnerships involved?
Oh, we had many wonderful industry partners. The detector came from an industry partner. The heat rejection system came from an industry partner. The mirrors for the telescope. So, yes, it is a wonderful collaboration. And sometimes whole subsystems came from industry partners. So absolutely, the JPL has focused just on the core element, that spectrometer, and some of the components for it are actually made here at JPL, but industry is involved throughout the process of building an instrument of this type.
And Tara on LinkedIn is asking about how to get involved. They write, how can a person like me who does not have a science background help with data sets? Is it possible?
That's a great question, and I think there are ways. I don't have any quick answers, but for example, we're going to be producing data products from EMIT, like you've seen the methane product, and there'll be a CO2 product, and we have mineral products. So even you could, with not too much effort, be able to download those products and see the distribution of minerals or methane, and then you might think about how to get involved and take advantage of that new information that comes from EMIT to address questions and areas that are important to you. But that's a wonderful question.
We also have a question here from Dee on YouTube that is wondering, are the scopes on EMIT using certain wavelengths on the EM spectrum?
Yes, we measure 285 wavelengths in the electromagnetic spectrum, starting from the visible, where our eyes see, well out into the shortwave infrared. So yes, we have, like you have a 3-color camera, EMIT is like a 285 color camera going into wavelength ranges that our eyes can't possibly see. Another interesting point is when I was in graduate school, I was trying to measure a spectrum like EMIT, and it took me about 10 minutes on a laboratory spectrometer. Right now in orbit, EMIT is measuring 300,000 spectra per second. So that's a spectacular thing for me to think about, going back to my graduate school days and what we can do today to achieve all these objectives that EMIT enables.
And speaking, going back to dust, Justin on LinkedIn is wondering, does this dust in the atmosphere affect communications to different spacecraft?
It can. There is now an era of optical comm where we're using lasers to communicate optically between spacecraft and the ground. So if dust was in play in one of those reception and transmission links, you could imagine dust would weaken the signal, and that would have impact on communication. It doesn't have so much impact on radio communication, and EMIT does use radio communication from the space station to get its signal down.
I think we might have covered this slightly, but Robert on LinkedIn is wondering, what is the effective resolution in area at Earth's surface?
So the effective resolution is for a single spectrum comes from about a 60 by 60 meter patch. That's the actual spatial sampling. But as I mentioned earlier, if you had just a 10 by 10 meter patch of a particular mineral and it had a unique spectral signature, we could say it was there. So we have sort of a spectral zoom to allow us to talk about constituents of the Earth system that are smaller than the ground sample distance.
And looking at the applications again, Jenny on YouTube is wondering, is EMIT able to track and interpret wildfires and their potential impacts?
Yes, EMIT and EMIT type measurements can contribute in several ways to understanding wildfires. We can map species type, which relates to burnability. We can look at the dry biomass, how much burnable material is there, and how much water is in the leaves. All those are spectral signatures that EMIT captures in this spectral range. So those would be things to tell you what the risk is. If we see a fire, we can actually say how hot the fire is very carefully and what might be next to it that might burn. And after a fire, we can look at burn severity. How Severe was the fire. How badly was the ecosystem damaged? And then into the future, we can look at how recovery might occur as we look at data sets. How are the ecosystems evolving after they've lived through a fire? So there are many elements for this type of spectroscopy.
Alrighty, so folks, that was the last question we had from the audience. We want to thank you all so much for those wonderful questions you had this evening. Rob is a wonderful and dedicated speaker, and we were so grateful to have him with us today. I want to remind you as well that if you have more questions about this mission, you can check out the link that's going to be posted in the chat as well as showing up on the screen right now. It's earth.jpl.nasa.gov/EMIT. So check that out, and thank you all for joining us. Thank you to our wonderful speaker, Dr. Robert Green, for joining us to discuss EMIT. I also want to thank our wonderful questions co-host, Jocelyn. Thank you for joining us. And I want to thank everyone working behind the scenes to make this possible. To all of you watching every month that take this time out of your day, we want to thank you and remind you that if you did miss one of our Von Kármán talks, feel free to check them out. They are available for the past 5 years on JPL's YouTube page. And please do join us next month for an incredible discussion about the InSight mission. Thanks again for joining us today, and we will see you all again in May. Bye, everyone.